Let's move a little bit into more realistic situations. So let's say you have two identical waves traveling in opposite directions. So you can write it as A0 cosine kx plus minus omega t. So one going to the right and one going to the left, and that obviously becomes cosine kx cosine omega t minus plus sine kx sine omega t. And they together can produce, if they are identical to each other, a standing wave, which is given by the form A0 cosine kx plus omega t plus A0 cosine kx minus omega t, which we wrote before as 2A0 cosine ks cosine omega t. These are very simple things to solve. This I took straight from Wikipedia, and you can see here the green and the blue waves are identical, and they are moving in opposite directions, and the red wave is having the amplification because of constructive interference of the two waves and destructive interference of the two waves. So you can see that it is stationary. It is a standing wave. So the maximum and minimum are happening here. It is anchored here, and the maximum, and then in the opposite direction, and so on. So fairly straightforward situation. There are many such examples in the real world where, let's say, the atmospheric winds go over a mountain which doesn't move. So the winds are forced to rise, and then on the leeward side you can have a wave that is anchored to the mountain because of the combination of background flow and the wind flow over the mountain, and you can get well-known standing patterns. They can also happen because of thermal forcing. Well, the mountain can act as a thermal forcing as well. Moving into more realistic interactions with the background state at planetary scales, we will just define k as 2 over 2 times a over n, which gives us n over a for wave number n, where a is of course the radius of the Earth. In this case, ka is an integer, so it becomes 1, 2, 3, and so on. So we have integral wave numbers. In mathematical physics, there is a approximation called WKB or WKBJ approximation, which is a technique for finding approximate solutions to linear differential equations which have spatially varying coefficients. Later on in chapter 6 and 7, when we look at real waves in the tropics, we will see how complicated these things get, and that's why we're looking for these approximate solutions. So we will just remember that and leave it here. WKBJ here are the name of the authors who discovered these things or developed these formalisms. The general wave kinematics in a variable basic flow, then you can write it the wave in terms of a exponential I alpha. Every time you have this exponential I alpha, you know that there are waveforms coming out of that. So that alpha is a function of spatial dimensions and time. So we are not saying here x1, x2, x3 as xy, j, xy, z, but we are leaving them general because waves can disperse, like we said, in the pond in all directions. In this case, omega, the frequency is minus d alpha partial t, and the wave number at I in direction I is d alpha dxi. Okay, this is the simple definition that explains the waveform here. Then when there is a background flow with V bar, then the frequency gets Doppler shifted. So this is the Doppler shifted frequency of the wave, given as the total wave frequency minus V bar I, again in the direction I, times Ki, the sorry, not direction I, but ith waveform Ki. Okay, so this formulation here is called Einstein Sum. So they are summed in the I direction, but the notation is not written explicitly, but this is just a sum. Okay, so omega then is a function of x1, x2, x3 as spatial dimensions, and wave number k1, k2, k3, and so on. So we can write that equation as del squared alpha del xi del t, which becomes, remembering the definition of alpha, minus d omega d kj dxi minus d omega dxi for wave number k. Okay, for all the other wave numbers. Okay, held constant. Okay, so because dxj dxi is just dxi dxj, we can write this previous equation 10.a as dki dt plus d omega dkj dki dxj, which is equal to minus d omega dxi. Simple manipulation of writing the variability of frequency in a spatial dimension direction as a function of changing wave number and wave number dependency on, frequency dependency on the wave number. So you can see how quickly things get complicated when we don't have these simple waveforms that are not in a background state, or the background state is quiet, steady, or not moving. Okay, so then the Doppler shifted frequency is the frequency minus this expression that we saw before, becomes omega equals u bar x times k plus omega d k. So this is now just moving this on this side, so Doppler shifted frequency plus u bar x k. So we have written this now in a general form as u bar x times the wave number. Okay, so this is again the equation we started with, and we wrote it as this way, and then this will lead to dk dt plus u bar x plus d omega d dk, where I'm saying d but it's partial, as you can see. This is the Doppler shifted frequency times dk dx equals minus k du bar dx. Why did we get this form? Basically, it allows us to look at the change in the flow in direction x and see how that modulates the waveform or the wave number and the frequency. Okay, so basically we are looking at the interactions between a wave with the background state. This is what we wanted to do. So let me leave that and then continue in the next podcast.